Thank you for coming to our presentation. First, I'll talk about Japanese medical device adverse event terminology. This terminology was developed by the Japan Federation of Medical Device Associations and it is commonly called JFMDA terminology. The purpose of developing it was to set standard terms for when writing the reports of medical device adverse events. These reports are submitted from medical facilities and medical device manufacturing companies to the ministry when medical device malfunctions occur during medical procedures. Before introducing the terminology, summarization of the reports requires a lot of time and effort because the details of the adverse event were written in free format. Introducing the terminology is expected to improve work efficiency and accuracy of report summarization and analysis to assist in reducing to adverse event numbers. The first edition of the terminology was published in March 2015 and consists of 89 terminology items such as for X-ray equipment and for biological information monitors. The problem with the JFMDA terminology is a variety of expression of preferred terms and synonyms for the terminology items. There are several reasons why the terminology items were developed independently by certain industry groups. We have been trying to map these terminology items to establish consistency in the JFMDA terminology. There are about 3,500 terms with respect to medical device programs, and manual verifications require great effort. In this work, it is necessary to detect and correct synonyms automatically using definition sentences to ensure consistency. This slide shows the results from the previous study. First, I'll talk about the outline of the previous research. We made 125 pairs of definition sentences of terms in medical device programs with similar or dissimilar labels. Using edit distances and word embedding techniques, we calculated the similarity, then conduct ROC analysis, and for the evaluation of automatic identification of similar definitions. The accuracy in edit distance was better than those by word embedding methods, and the edit distance were useful for similar definition sentence pairs with common phrases. However, occasionally word embedding methods found similar definition sentence pairs with different phrases. This table shows examples of similar definition pairs and the accuracy of the automatic prediction. Blue letters are different strings in two definition sentences in a pair. If there are long common phrases in the two sentences, the edit distances predict them to be similar. However, the strings in the third pair are different, but Dr. Beck predicted them to be similar. This is an interesting finding, and we thought it necessary to find and identify the features of the pairs of synonyms and the different meaning evaluations. Now I will explain the algorithms of Word-to-Vec and Doc-to-Vec. The Word-to-Vec is an algorithm for expressing the concepts of words using hundreds of vectors, and the algorithm uses a two-layer neural network model to learn word associations from a large corpus of text. There are two architectures, skipgram and SIBO. In SIBO model, the distributed representations of the context or surrounding words are combined to predict the word in the middle. In the skipgram model, the distributed representation of the input word is used to predict the context. Here is the concept of doc-to-vec. The doc-to-vec is a method for expressing the concepts in documents using hundreds of vectors, and it is an extension to Word-to-Vec for learning document embeddings. The DEVO works in a way similar to skipgram. In the DEVO architecture, with the order of words in the document disregarded, the DM works in a similar fashion to that of SIBO. For the input, DM introduces an additional document token in addition to multiple target words. However, unlike SIBO, these vectors are not summed up but concatenated. One of the methods of identifying the features of vectors visually is using TSNE. The TSNE is an algorithm to reduce dimension based on the equations here, and it is useful for visualization purposes to capture complex high-dimensional patterns. Summarizing the above, the purpose of this study is to identify the patterns of the vector distributions in definition sentence pairs using TSNE. This slide shows the flow of this study. First, we collected about 600,000 definition sentences with the JFMDA terminology. Next, we created 125 pairs among the definition sentences with similar or dissimilar labels determined by 3 specialists in medical device safety. Computing sentence vectors in Word2Vec, an average vector was calculated using vectors allocated to each word in the definition sentence. In Doc2Vec, sentence vectors were inferred using the Genshin package in Doc2Vec. Finally, hundreds-dimensional sentence vectors were mapped onto a two-dimensional vector space using TSNE. Now, I will move on to the result section. These figures show the distributions of sentence vectors. The distributions in Word2Vec with skipgram tend to be wider, but there are clusters only found in Doc2Vec. This is because Word2Vec calculates the average value of word vectors, so the characteristics may be less distinctly identified, while the Doc2Vec plot tends to form clusters in sentences with common characteristics. For true positives, the vectors of the sentences tend to be closer to each other in all models. However, vectors in Word2Vec with skipgram were farther apart than in the other models. For false negatives, sentence vectors are most closely clustered in Word2Vec with SIBO and Doc2Vec with DM. This tendency is strongest in the TSNE of Doc2Vec with DEVO. We think this is the reason why the sensitivity of Doc2Vec with DEVO has improved to show the closest arrangement. In addition, the spread in pairs of definition sentences was larger in DEVO than that in DM. With false positives, the pair of vectors tend to be farther apart than with true positives in our models. This slide shows examples of the vectors of sentence pairs with true positive focused by Word2Vec with skipgram and Doc2Vec with DEVO. When comparing Word2Vec with skipgram and Doc2Vec with DEVO, Doc2Vec with DEVO made some clusters of similarly definition sentences. The definition sentence example also suggests that Doc2Vec with DEVO is better at detecting sentences with similarities. This slide focuses on the map of Doc2Vec among the false negatives, comparing the DEVO and DM plot. The pairs of similar sentences in the DEVO plot more closely to each other. The bold letters indicate those. We think that it is necessary to investigate the cause of not being true positives together with the cosine similarity in future work. In the true negative pairs of our models, the vectors were distributed widely. In Doc2Vec, there were several clusters. In these clusters with the dotted circles, we found two features: presence of identical definition sentences used in different definition sentence pairs, and definition sentences with the same phrases for other matters. The reason for the former is that the vectors of the same document are slightly different in the inference of the vector by Dr. Beck, or it may be due to calculation errors of TSV. In the latter, some cases were detected as true negatives. Here are examples in sentence vectors in clusters. Calculation errors are shown above, and a false positive pair is shown below. In conclusion, we visualized the distribution in vectors of definition sentences using TSNE. Compared with Word2Vec, similar vectors in Doc2Vec were closer and formed some clusters. Vectors of definition sentences with true positives and similar meaning located closer in a vector space Doc2Vec with Vivo. In future, we plan to conduct further examinations with other parameters such as cosine similarity. Thank you for your attention.